I would like to give you a very short overview of what our group is doing in Kharkiv. The group is the ion cyclotron group in Kharkiv, and what we're ICRF is ion cyclotron range of frequencies. People also very often use ICRH, which is ion cyclotron resonance heating. I prefer to use ion cyclotron range of frequencies because it just says that it's not just resonant frequency, it's a way of heating the plasma, and it's a range of frequency because we can use other method than just the cyclotron resonance. It is the range of the cyclotron resonance, but it is not exactly this ion cyclotron resonance. And I also like to refer to it as ICRF rather than just ICRH, because I think with this method we can also do more than just heating. We can do also other things than just heating. We can do current drive, we can influence the transport of particles, so we can do a number of other things. So just remember, ion cyclotron range of frequency, ICRF. Our group does a number of things, and about 2/3 of our work is concentrated on ASIC subgrid. ASIC subgrid is a tokamak in Kharkiv. 1/3 is divided up evenly between ether and jet and demo. So we're working mostly on a tokamak in ASIC in Kharkiv, and then the rest is, we'll say, the larger machine, jet, which is existing, ether, which is being built, and demo, which is rather far in the future. This is an overview of ASIC subgrade. You can see a tokamak, and as many tokamaks, you can not see the tokamak. What you see around it is mostly diagnostics, heating methods, fueling methods. You have here our system, which is the lines that bring the power from the generators to the machine. You see here, this is a neutral beam injector. There's a neutral beam injector on the other side. This is optical transmission of the electron cyclotron, resonant frequency heating. A number of other things are diagnostics. You can see here, this is a charge exchange diagnostics, and here in the back is spectroscopy. There are a number of other things. So mostly, if you look very closely, you can see here some red beams, and the red beams are part of the structure which hold the colloidal field coils of the tokamak together. The power of our generators is coupled to the plasma through antennas. In ASIC subgrade, we have 4 antennas. This is a horizontal cut of the machine. You can see here the ports, and we have 4 antennas. Each of those antennas have 2 straps, and you can see here 2 antennas side by side. So this is one of the side of those antennas. Now if you look at the system, before you get to the antennas, you have to transport the power to the antennas, and you have to produce the power to the antennas. And I have schematically put this in this way. You have the plasma here, you have the antennas here, you have the transport of the power from the generators to the antenna. So now let's go step by step. The step by step, this is the generators here, and I'll come into details about the generators. Then we have here the lines and the transmission lines and the matching. What you have seen on the previous picture, everything this was orange, was all our system. It was a very clever decision at the beginning to choose this color because it's very prominent. Then we have the antenna in the machine, which we have already seen. And then you have the plasma. Here you have the plasma, and you can see here again some of the antennas in the background. Now, going back to the generators, I have said generator, but actually there are a number of generators. This is the final stage. The final stage is about 2 megawatt, and it has a height of something from here, the bottom, to the top of the pictures there. So this is the size of this generator. This is the final stage. The final stage of a series of amplifiers which actually start with 20 milliwatt. 20 milliwatt is first amplified to 100 watt, then to 4 kilowatt, and then to 100 kilowatt, and the last stage brings it up to 2 megawatt. So we have a chain of 4 amplifiers. The active part in the final stage is a tetrode. You're all very young, so you may not know what a tetrode is anymore. Now everything is with transistors and chips. But before, if you had a radio, you would have in a radio you would have tubes like this, and this is a tetrode, and it's used to amplify the power. Now this is the type of tetrode you would find in those radio amplifiers, but the one we have here in these generators is a little bit bigger, and you can see this is the size of the tetrode we have in our generator. So a piece like this costs about 100,000 euro just for the tetrode. Now coming back to the next step, the transmission lines. The transmission lines, essentially you have to transport the power from the generators to the antennas, and this is shown schematically here. You have just here transmission lines. Here the power is split between 2 antennas, and you have here a matching system. Now the way the power is transported is through coaxial lines. It's not because the frequency is low. You cannot transport it with waveguides. You have to transport it with coaxial lines, which is just like the cables we have between your satellite dish and your television. So it's coaxial lines, except that our coaxial lines are about this size. So we have 4 of those. We have 4 generators, each with transmission lines connected to the 2 straps of 1 antenna. Now at some point we had to change this, and we had to combine 2 of those. And the reason for this I will explain to you briefly. It was a very big step in order to be able to put the power into the plasma. The reason for that is actually that you have, and this is where this matching comes in, the impedance of the antenna is about 2 to 3 ohms. The impedance that the generators wants to see is 50 ohm. So you have to adapt the 2 ohm to the 50 ohm. This is done with putting here in parallel impedances. Those are short-circuited transmission lines. Now when I say that the antenna resistance is 2 to 3 ohm, I'm saying it a bit too short, in the sense that the antenna impedance depends on the plasma. And for certain condition of the plasma, it's 2 to 3 ohms. But in the plasma, if you have a plasma with an H mode, you have instabilities in the plasma edge. Instabilities in the plasma edge which change the density of the plasma very quickly and very substantially, so that the coupling here, the antenna resistance, can vary very suddenly. Within 10 to 20 milliseconds, it can vary between 2 to 8 ohms. Now, this is a mechanical system. It can never adapt this changing resistance here to the 50 ohm. So what happens is that you have reflected power going to the generators don't like it, they shut it down. So we could not run the generators. So the solution then was the following. We have inserted here in our lines 3 dB couplers. 3 dB couplers have the property that if reflected power comes back here and here in the proper phase, then the power is not direct here, but goes to a dummy lobe. So which means that the antennas here could have a varying antenna resistance. The power, the reflected power, because it's not matched properly, would not go back to the generators, but would go back here in the dummy lobes. And this helps substantially, and you can see it in this view graph. We have here the antennas, we have the matching network, and we have the couplers. This is the instability in the plasma, which we call ELMS. So this is the very fast and strongly varying density here in the plasma edge. This is the power coupler to the antennas. This is the reflected power at this level, in those lines. For 1 megawatt, we have 100 kilowatt of reflected power, 10% coming back. This is due to those variations. And because of those 3 dB couplers here, the reflected power at the generators is 1/20 of this, only 5 kilowatt. And with this reflected power, the generators can cope, so they can continue to work. This was a substantial point in order to be able to bring the power into the plasma. Now the next challenge we are facing now is actually the antennas. The antennas, the substrate has a wall that is completely made out of metal. It's actually made of a heavy metal. It's made of tungsten. Every first component of the plasma wall is covered with tungsten. Now, the properties of the antennas are such that if you have a parallel electrical field in front of the antenna, those parallel electrical fields can be rectified. If you have rectified those fields, then the impurities, or say ions, will get accelerated in this rectified sheet, in this rectified field, and will impinge on the wall and will sputter material from the wall. Now, if the material from the wall is made of a heavy metal, then you get those impurities coming from the wall, and you come into the plasma, and then they will start to radiate. So we had, when the wall started to become made out of heavy metals, we had those impurities, and this made life more difficult to work with ion cyclotron. The way to proceed is to reduce those electrical fields, and here you see a picture or a calculated value of those electrical fields generated by the antennas. And you can see here, I mean, the cause corresponds to the level of the electrical field here, and this is a measure of the rectified electrical field, so this is a voltage. For this antenna, you had very high voltages on those field lines, which accelerate the particles and produce those impurities. We have an intermediate step produced a small variation of this antenna, and just in order to show the concept. The concept here, you can see that we have reduced those electrical fields and also the voltage on the field lines. And the next step is actually an antenna which is much further optimized, which is more complicated to make. This was a slight modification. This is a completely new antenna where we have reduced those fields substantially. So this is the steps we are doing. This is the original 4 antennas in the machine. In 2011, we have kept 3 antennas as they were, but we have modified 1 antenna. So you can see here, we have modified 1 antenna with a much wider side. And indeed, with this wider antenna, we could show that the accumulation of the impurities started much later. So with this antenna here, the accumulation of the impurities started later than with the normal antenna. So it proved that the concept was valid. So this was in 2012. We have this reference antenna, modified antenna, and what we did is the 2 other antennas we coated with boron. So that's not to have the first wall as impurities. The antennas were coated with boron, and those indeed show that the antennas which were coated with boron had a much lower impurity production. Here you see each time we put on those regular antennas, we have an increased production, and each time we put on those antennas with boron coating, we have a reduced impurity production. This shows indeed that the impurities do come from the immediate antenna neighborhood, and it also shows that if we optimize the antenna with respect to those electrical fields, we can reduce this impurity effect. So this is now the next step we'll be going to do. 2013, after having shown that indeed the logic is correct and that we can do those steps, we will have 2 antennas which are completely new and will be with 3 straps. This is in cooperation with China and with Italy. In order to further investigate the production of those sheet effects, sheet rectification, we will building a test stand, which we call Ishtar. This is for Eincyclotron sheet test arrangement, but Ishtar is also a monument from Babylon, which you can see in Berlin. And the idea here is to produce a plasma and have the possibility to, independently of the tokamak, investigate those production of sheet effects. So this is actually something which used existing equipment but is modified and is meant for students to do PhD thesis, doctoral work and master work on it in order to better understand this impurity production and impurity generation. We also have another experiment which is here, which we call manipulator experiment, and this is to investigate arcs in the transmission lines. I mentioned that in addition to ASIC subgrade, we're also working on JET. Here you have a picture of JET. JET has 4 set of antennas with 4 stripes each, and then 1 additional antenna which is more of the ITER type. On ITER, this is ITER. There will be 2 antennas which will be inserted in the antenna plugs. Note here the little man. And this is the ITER antenna. The ITER antenna here is about 2 meters high. Will have a power capability of 20 megawatt per antenna. Components of the antenna are actually here. We have 8 times 3 straps, and one of the largest difficulty in ITER is to get all this piping and all this. You have to shield the neutrons, so you have to put a lot of water in there. So it's everything is very tight within this board. So let me finish here with a small view of what we hope, how things will work in ITER. This is the ITER vessel. And there you have 1 antenna, which is producing the wave, and you can see here the wave as it is being excited and propagated into the plasma. You can see here how the wave decreases as it goes into the plasma, and also as it goes around. It's localized within a certain area of the antenna. Now let me finally conclude. We have a Kharkiv, one of the most powerful system worldwide. We have 8 megawatt installed. We are only beaten by JET, which has 2 megawatt installed. But we are one of the most successful. We have put in 7.2 megawatt, 90% of the 8 megawatt. We have a coherent integrated program which focuses on the major aspects: impurity problem, which I have mentioned, the heating, the central power at high density, and I mentioned here, but I could not go into much more detail. We can do also other things than just heating, influence rotation, we can look at fast particles, things like this. We need for this, and we have a very solid infrastructure with unique test stands like Ishtar. We have a very tight link between physics and technology. We have close contacts with universities, and we want to put increased emphasis on master and PhD work through our test stands, for example. And we are solidly embedded in worldwide cooperation with effective support from guests. Italy, India, generators, texture, wall conditioning, China, Italy and France, which are building our new antennas, Belgium, sheet effects, and Ukraine, I hope, for further increased cooperation. Thank you.
Вопросы есть? Есть у кого-нибудь вопросы? Да, пожалуйста.
In order to increase the impedance of the antennas, we add another antenna in parallel. Will that increase the impedance?
No, it's not to increase the impedance of, both antennas have their own impedance. The impedance is affected by the plasma. In order to be able to use this 3 dB coupler, which in fact moves the reflected power then to a dummy load, you have to have the variation identical and in the proper phase. That's why you need to do antennas. So putting the two antennas is not to increase the antenna resistance. What we have at the beginning is we have the antennas and we have the matching in parallel. The antenna resistance is typically 2, or if you have almost 8 ohms, but you have to match it to 50 ohms. Now, when you put impedance in parallel, is that what you mean? If you put impedance in parallel, depending on which impedance you put in parallel, you can actually transform it to 50 ohms.
Еще вопрос.
Could you tell me please, what is the modern state of ITER program? I mean, when it will start to work, really?
Well, I mean, I'm not quite the right person to ask this. We're providing a component to ITER. I can only tell you what the ITER director has told us at the recent meeting.
But maybe you know.
The recent situation is that the machine will start operation 2019-2020. It will start operation in a simple way, just with hydrogen, etc., etc. After a while, there will be some modification, and it will take a while before it starts really with deuterium-tritium. It's not 100% clear yet, because there's some decisions still have to be taken in terms of which diverter it will start. I think the official state is that the diverter is still starting with graphite diverter, graphite tungsten diverter. But in order to save it, that would mean that if you want to then move to deuterium-tritium, you have to change the diverter to a tungsten diverter. Now, many people push to start immediately with the tungsten diverter, not to have this intermediate step of starting with carbon. The reason to start with carbon is that people feel more comfortable with carbon. With carbon you cannot use if you use tritium. If people start being more comfortable using tungsten from the beginning, they will just leave out this step and start with tungsten from the beginning. That's the general status.
Еще вопрос. Last question.
Is there an opinion or solution to use Geratron as power generator in your system? You use 4 generator cascade, but it's maybe more interesting to use Geratron as a generator for
very fine.
The frequency we operate with is the cyclotron frequency of the ions, and with the magnetic fields we're operating at is typically 30 to 100, 30 to 60 megahertz. This is the frequency we're operating at. Gyrotrons is if you work at the electron cyclotron frequency, and then you're in the 100 of gigahertz. So much smaller wavelength, and ICRF does have gyrotrons. One of the heating system is also electron cyclotron. I showed the transmission, optical transmission line dock in Armenia, and about 4 megawatts is installed with gyrotrons. They come from Russia, by the way.
Все, вопросов больше нет. Спасибо большое. 5 минут.